So, hello, welcome everyone to our weekly seminar of mathematical physics. Our speaker today is Ján Pulmann from Charles University, and he's going to tell us about propagators, homotopies, and Lagrangian relations. So,
thank you very much. Thank you for coming. It's very nice to be back. It's a joint work I do with Brandon Magnesica, and I'm still doing with Brandon Magnesica. So part of that you can find in our latest paper archive, it's recent archive, and part of it is new stuff. And I will parse the all. And part one is a review of the relationship between these three notions. Title concepts. And part two is generalizations. So first part is really kind of standard. There's two experts. It appeared. And probably Cardani and Mio and Costello will be the correct people to where it's kind of like this specializing in the early 2000s. Okay, so let me compute the only integral I can compute. So let's with the model Gaussian. I'm normalizing. So how one can do this? So you can add b here, and you have to then differentiate with respect to b and times. Send b to 0. I can complete a square in the exponential. So it's e to minus 1/2 ax squared minus 2b x plus b squared root 2a. X, and then the term which we added with remove, so it's kind of e to b squared over a. This is just because you can just shift the integration by a constant. This integral is the same as just integral of minus 1/2 ax squared. So this whole thing is just the expectation of 1. So, and if you take a derivative of here, this also non-zero and is even and it's 2k, and what we get is 1.
sorry, should I get some? So, I mean, should we rescale the? Don't get like squared away somewhere.
It is hidden in the expectation value of 1.
Okay.
Yeah, here is just really a shift of the integration. Then there are some combinatorial factors. If you differentiate here with, and you get 2k factorial for all the ways this differential operator can hit this b to 2k, and you divide by k factorial from the exponential. This is the answer. Hopefully, I didn't check it with anything. And how you can write this down as follows. So this will be the basis of the formula I will be writing through the code. Let me just rewrite this. expectation value of x to the n can be computed by acting with this differential operator on x to the n.
Power.
Yes. Thank you. All right. And maybe we can write this. Finally, write this is e to 1 over 2a d squared x. And like what you do here, we have to invert this a 1 over a and write it next to a second order differential operator. Okay. So in quantum field theory, or maybe in discretized QFT, we want to compute moments of multivariable Gaussian. So let me now write the Euler formula where x is maybe a polynomial x, where x is now an element not of R, not of some vector space.
Sorry, I don't understand. I don't understand it. Do you hear me?
Yeah, I hear you.
If n is 2k, if we suppose that n is 2k, then at the left-hand side, then at the right-hand side, k is then independent. K is 0, k is 1 at the sum in the.
Yes.
So if we take k is 0, we get xn at the right-hand side, and there is no xn power n at the left-hand side. So I'm a bit confused, but.
So sorry, maybe then I can write k prime here.
Okay. Yeah.
And where
Okay,
is
thanks.
and the k then is the
K is n over. K is n.
okay.
Yeah, yeah.
And do you have a single or double factorial?
I think this, if you combine the 1/2, the 2k and the k factorial, there's the double factorial. It's
Okay.
yeah. Sorry, like here you can add all the differential operators together, but only one of them will give non-zero contribution when you act on one single. But if you wanted to compute expectation value of a polynomial, you would act with this whole differential.
So we must evaluate at 0, probably. We must evaluate at 0.
That's correct.
Yeah.
Oh, yes.
Yes, thanks.
And infinite differential operators are not called differential operators, but that's
Okay.
that's
What
minor.
would be a good name for this operator? It's an true. It's an infinite order differential operator, but on every operatable on every polynomial, there's only finite contribution. So let's one way to understand.
Okay.
Let's say this is some kind of vector space, finite dimensional vector space for simplicity. Polynomial, and now A is a symmetric matrix. And now let me write the same formula without justification. You will see in a one-dimensional proof that this is equal to should equal to 1/2. So exponential of 1/2 of d of some second order differential operator, which I will call dp, acting on x to 0 times the. Oh, yeah, and I also drop the one should also the execution value. This is the factor which contains pi square root operation.
Wait, sorry. So what is the difference between V and V0?
Yes, v is good.
And why is x? Wait, there is no x on the right hand side. There is x on the left hand side.
Okay, so then, yeah. Can erase the x. It's, yeah.
Here?
Yeah, here it is kind of variable.
Yeah, so it's just like
That's the function of x.
it's like k of x or something. K of b. It's a function. F is a point of a function. Yeah.
Is it some continuous version of all the chains?
No, I think this is extremely general. This is any.
They will be not inverse of some capital X.
No, this is no. Probably that should be like n minimum block and finite imaginable discrete division of QFT. But no, in general, this is like it's a vector. It's any QFT. Okay, and how you compute this second order differential operator? So it's VP. So maybe I would call this the propagator. But I'm not. I forgot most of my QFT, so maybe if there are people who know it better, then tell me there is a different name. But B is a second order differential operator. This is you take the matrix A, you invert it. Actually, IJ component of the inverse. It's clear so far. Feel free to stop the questions.
Maybe you should write it explicitly second order.
And just write the words, or I can write like this. B is A inverse IJ. This were called VXI, VXJ, where for some linear coordinates of X. On these things. There's probably 1/2 somewhere. So this is correct,
No,
and there is 1/2 here.
you did put 1/2 in there.
Okay. Then there should be probably 2
Okay.
of symmetry. Yeah. That's not very important. Okay. So if you want to talk about gauge theories, one option is that you can fix a gauge, but at least here we like to do button-located formalism instead. Because you EV, what does it mean that is schematically? I don't want to get into. I want to give an introduction to EV. What it means that we add more fields. So instead of V0, we consider V, which maybe is something like T star -1 or V0 and maybe plus some shifted the algebra like this. But it's not very important. The point is that you exchange, you go from V0 into a vector space V, which is -1 shifted. Symplectic. This is a symplectic, linear symplectic form of degree -1. We have to extend the action.
We take the shifted tangent model of the whole thing, right?
Yes.
But it can be anything which is easy.
Yeah. Like this is only an example. E.g. Extend this action with -1/2 x to something which I call so far maybe just the free action.
So the example actually needs to be like BRST and on it
B, yeah. So this, so the G1 will be VRST and this would be B. Okay, now we we do an integral over only half the field. So we can compute an expectation value of f. We take an integral, not over the whole of V, but we take the Lagrangian submanifold. Okay, here, instead of writing dx, the correct thing to write is a square root some of the Lagrangians. The space. It's just if you have something integrate over a Lagrangian, you need to integrate the half density because the half density on the space V gives you a density on a Lagrangian. That's the correct geometric thing to consider. And then one can write a similar formula. We e to 1/2 some differential operator, secondary differential operator p, which depends on this L, and now we acts on f, and then we set where it's dp of L is given by you take this quadratic action as free, you restrict it to L, and then you invert. So that's one of the also advantages of patternless formalism, that if some conditions are satisfied, you are kind of free to choose this L. And then you might be able to find L where this is non-degenerate, even though it may be here, if you take the base of the bundle, S3 will be degenerate. So that's one of the points of pattern homotopies, that it allows you to do this choice of L, which is like a choice of gauge fixing such that you can compute, you can do perturbation. But sometimes one cannot find an L on which S3 is non-degenerate. So by inverse, I mean this is really a matrix, so we can take it's a matrix inverse. But sometimes you cannot find L where it's non-degenerate. I don't know what to write. I don't want to write this whole sentence, but L. So first, there is a way to parameterize how big, like what was the size of the problem, and it was as follows. So let me introduce some notation. Functions of B, they are a BV algebra because B is a BV vector space. So we have a BV operator delta, degree 1 squares to 0, second order, and we have a hot Boston bracket as an operator. We can compute an operator which looks like this. This is quadratic, the bracket is constant coefficient, so this is actually a map which goes from B dual to B dual. If you apply it on a linear coordinate, you get a linear condition of linear coordinates. So you can consider this to be the transpose of some differential operator, of some linear operator on B. And there's a condition we put in, which I didn't write down, the classical math equation, which says that U square is 0. It's equivalent to classical. And we always impose this. And there's a right effect. The largest subspace on which S3 is non-degenerate is of the size of homology of Q. Symplectic orthogonal. Okay. This is slightly imprecise statement, but the dimensions are correct.
But how do you define? I mean, what does it mean to take a symplectic orthogonal?
You need to choose an embedding of your homology inside to see the symplectic subspace of the space B, and then it will be like half of the complement.
With the size of like the whole space minus the dimension of the.
Yeah. But even like this, if you embed this, like if you put like a tilde, which means that it's embedded inside B,
Okay.
then you can take the symplectic orthogonal, which will be a complementary subspace, and then the Lagrangian in this subspace for which you can dictate in the complement.
Okay.
I will come back to these things. I will actually write down some definitions again. But okay, how to read this? If the homology is 0, it means that you can find the Lagrangian on which it's non-degenerate. Because if this is 0, then the complement is everything. If the homology is not 0, then you cannot find a Lagrangian. There's something you can do. So what can one do?
And is it the entire homology or just like some degree?
The entire homology.
The entire.
Yeah. Yes. Could you please move up the border a little bit because online people cannot read the now. Now it should be fine.
Thank you. Maybe I can do this now. So what can one do? So in this case, you don't compute numbers, expectation value, but you compute functions or how densities, which are called effective observables. So instead of the number expectation value of NF, you compute a half density okay, and what you do is E X integral. There is a normalization. Okay, and now over what you integrate is something that I call I, where I, the subspace is V, is an isotropic subspace. Right, meaning that the symplectic form vanishes on the space, where S3 restricted to I is non-degenerate. And what you get is a half density on the so-called isotropic reduction with respect to I.
So you would like to have still the S3 or
No, so I actually want S. You should think as that. You should think that I edit S. I edit interactions to the action only to make this formula kind of for it to be the thing people call effective observable. It's not very important. You can think of exponential S interaction as being part of what we call before that. It's not that. It's not important for the formulas, but for physics interpretation, that's important. Maybe this is cool. This and here.
at the moment you don't assume anything about the Z? That can be any, but just essay to solve.
Yes. Yes. Those are only somewhat are physical observables. They have to again satisfy some equations. But this equation work makes sense for them.
Now this can be something of the quantum.
Yes. Okay. Yes. So for this to make all physical sense, we want that delta E to S is 0. And here E to W is the integral E to S. That's called the effective action. And it also satisfies its own quantum mass equation on the reduced.
There is like V1 half V state, right? You just,
Yes.
and that's okay.
Maybe here that.
So it's also confidence.
Yeah.
Yeah, everything is an outlet if you put what you put down to an integral. So,
Well, the result also will be a half radius attendance. Reduced situation.
Yes.
oh, there is an easy way to. Oh no, this is. Maybe so to recap what just so far happened is that choosing a non-degenerate isotopic subspace, right? If we want. This is what a non-degenerate isotopic subspace is. The isotopic subspace where S3 restricts to a non-degenerate full form. Which means that you can take the inverse, is a propagator, and it allows you to compute these effective observables. And if the isotopic subspace is actually Lagrangian, then what you get is not an effective observable, but you get actually an expectation value. That's numbers.
Maybe that naive question, it sort of naive physics, you would expect that you should always be able to get a number in some way at some end. But you're saying here that in order to do that, you're going to need that the homology of the.
Yeah, I think yeah. So this is what people call existence of zero modes. And what I think my understanding is that you cannot just get a number, you have to make additional choice of something which allows you to integrate over the zero modes.
Unless you put 0 at the end, one of the zero modes. You compute it, you get it, and then you put all the variables on homology to 0. You get a number.
I see. Okay. I don't. Yeah, I really think what that means.
But you're saying that in physics, this would be kind of reducing down to 0 modes or something.
Yeah. Yes. But I think we need some kind of additional choice. Maybe that's what people call picture changing operators or something.
Sure.
Or couple. Yeah, maybe physicists will always say couple with some system on zero mode. But I couple with some system on zero mode or something like that.
Okay.
But yeah, I will ask some physicists I know about how to do this.
That's already good. Thank you.
Okay, so I will maybe say that there is this. So this is what we want to call physics. This is what one could call geometry. So let me write algebra. a proposition. Maybe in some form it was good, but like we're saying that it's an equivalence. That's what we did. So given a symplectic space with this quadratic action, there is a one-to-one correspondence between non-degenerate isotopes, isotope subspaces, and linear operators K of degree -1 is the opposite of the degree of the differential. It's important. Such that it's self-adjoint because there's a symplectic force. You talk about adjointness. It squares to 0 and satisfies this K, Q, K is equal to K. Recall that Q is the difference of the matrix. You just create out of this. Okay, that's the end of the proposition. This bijection is there is explicit. The isotopic subspace will be the image of K. You get that KQ and QK are projectors. You can actually write down V as image Q plus image K plus image of 1 minus Q minus K. For that, I will need to put it up. Very great. You have a projection onto image 1 minus KQ minus QK. And this is a homotopy equivalent. Of chain complexes, even if it's something stronger, it's a thing called, which people call special deformation effect. K is self-adjoint. This makes it compatible with everything. Yes. So in this decomposition, this is a symplectic subspace, this is a symplectic subspace, and these two are orthogonal. Sorry, these are two are complementary Lagrangians. And this just follows all from this K plus. And it's also easy to write down the propagator in this setting. E, which is now I can write the function of K, is just the commutator of the VV operator with K. K is a linear map from V to V, which makes the, and you can extend it to a vector field on V. That's what I mean by that part.
Everything is okay. Commutator
Yes. Yeah, the commutator is K, so it's an anti-commutator. And also, that also reminds me that I wanted to mention that you can talk about propagators also in non-BV world, but this formula only makes sense in the BV world. So that I like this formula because it tells you that you can equal propagator in many different ways, but for that you need to go into BD because this is